Okay, so today I'm going to discuss about the Green's function. So I'll just briefly introduce the Green function and I will discuss this Green's function method for the Laplacian operator. So um, let me start with some basic introduction. There are several problems in our physical chemistry. Basically, not problem, differential equations for the physical chemistry. We know that just like we can take our we are very familiar with this type of equation actually, like Laplace's equation, then Poisson equation, Helmholtz equation, and diffusion equation. These all equations are differential equation basically. So these equations, Green function is used basically to solve these kind of equations. So the method is very useful method, and we know this in condensed matter physics. This Green function method is very much useful method and well used method actually, this Green function method. So today I'll just introduce the form of the Green function first, then we'll solve the Laplace equation, which, because this is the most easiest we can say. So we can solve not Laplace, Poisson equation. Poisson equation also holds the Laplacian operator. So we'll solve the Poisson equation in 3D, especially in three-dimensional case. We can also discuss in D dimension. I will discuss that in the last part if time permits. Otherwise, we will solve the Poisson equation in three-dimensional by using the Green function method. Okay, so let me introduce the basic form of the Green function. What is the Green function? Let me take any differential equation. This is a differential equation. This is basically inhomogeneous, linear, ordinary differential equation. Just we can think like this ddx of fx, like dx is these things. We can write in general like this dx fx equals to dx. So this is a ordinary differential equation. And let's say this equation is valid on the interval between a and b when x belongs to a and b. In this interval, this equation is valid. Now we have to solve this equation. So by using Green function, we'll define what is the Green function, and then by using Green function, we'll see how we can solve this kind of equation. So basically, Green function is not a unique function. Depending upon the differential equation, which kind of differential equation we are choosing, depending upon that, the form of the Green function will be also. There is a general form, obviously, but for different kind of equation, we will have the different kind of Green function. So we'll look at it. Now, this equation, if we uh, convert this equation into an abstract space, then we can write it like this. We know that fx is equal to xf, where f is in the abstract space. So similarly, we can write gx equals to xg. And in abstract space, dx, we can write as just d. We can think in terms of operator as well. So our equation, let's give it number one, equation number one. So equation number one, we can write as d of f as g. Okay. Now we need to find out, solving this equation means we need to find out the value fx. This this is a output of this equation after solving. So now we can write it. F is just d inverse of g in this form. But this is not the whole thing, because we can, in general, we can write this like, okay, how we can define this? This is a general form, because let's say if we apply here d operator both sides. If we apply d operator both sides, then we obtain d inverse. So essentially that is identity, which is leads to g. and here not here. So it is dhi. So here dhi is 0. If d of hi is 0, then we can add this term here. This is a general form actually. Okay, so this means hi is the hi linearly depends on x. We can say like this. Then we will have this d of hi is 0. So let me write the exact term here. Ci are the constant, C are the like coefficient, and hi basically linearly independent of x. Then if it is differential operator, let's say if d is the ddx, then this will be 0 anyway. So this form is the general form we can write. Now from here, if we project x, then it will be x d inverse g plus summation over I ci x over h, x and h. Okay, so we can write it in function space again. Fx is equal to, let me write it like this right now, and this will be ci hix. Okay, so now this term x d inverse g, can write it x. We can introduce the identity operator. So then it will be like d inverse square. So it can, let me write it in the integration form. It will be then d inverse, because this is the continuous basis. So we write like this. So this is basically the identity operator in continuous basis. We know this. Okay. So now, so it can be written as a to b so this is gx, there is no confusion, and this part is written as the green function like this. This is the green function. So this equation will be essentially fx is integration a to b dx inverse and prime dx prime gx prime gx plus plus this part c summation over c h over x. So this is the our form of fx. So this is our green function, which is defined as gx x prime defined as x, x t inverse x prime. So this is green function. Let me write it of operator dx. You have to mind it. If dx change, then this green function will also be changed. So this is the green function. Okay. So let me stop it. Now we have to evaluate this thing. What is the green function? This thing. Now you can write. So as this is the green function, we have written already. But we can think like this. So if we write it d inverse x prime. So d inverse is identity. So it will be essentially this, and it is just the delta function. Okay. Now this part also can be written as, if there is any doubt, then please stop me and you can ask. So it can be written as dy x dy y d inverse x. Just I have introduced these things dy y y. This is also identity, right? So this identity I have just introduced here. So it will be dy. So this is differential operator. We can take it out. Then it will be x and y, and the green function y x prime. If it is so, this gives us the delta function. So it will be dx delta x minus y g y x prime. So essentially, this function will survive when x equal to y. Otherwise, this delta function will be 0. We can write it dx just g x prime, because delta xy equal only survive when x equals to y. Then overall integral will convert g y of x prime to x and x prime. So this also can be written as dx equal to dx into g green function of x and x prime. So it equals to here with delta function. So it is equal to delta x minus x. So this is another important relation we obtain, that dx g x prime equals to delta of x minus x prime. Okay. And if we remember, our main equation was also like fx equals to gx. This was our main equation. So if this is our main equation, then directly we can write down this equation for the green function. Now, if we solve this equation, then we can obtain g, the green function, and if we put that green function here, then we can obtain the fx. This is our total method, the procedure. So let me deal with one example. Let's take the Poisson equation. Right. Okay. The general form of the Poisson equation like this. Now we will discussing the three-dimensional case. So in three-dimensional case, so we have to take the vector r vector. So fr equals to g r. This is our Poisson equation, and fr equals to 0 when r tends to infinity. Then fr will be essentially be 0. Okay. Now, if this is the equation, then what will be our green function equation? This equation, we can write it in similar way, just del square, because if we see here dx will be there, same dx. So here dx is the Laplacian operator del square. So here actually dx is equivalent to Laplacian operator del square. So we can write it g of r prime, and there will be 3 for the 3 dimension, and delta function of the third order 3 dimension. So essentially this will be the form if we tally with this equation. So here this is for 1 dimension. So essentially there will be 2 more dimensions in 3D case. So these are 2 equations, and what is the main equation from where we can evaluate the FR? This equation for 3 dimension, we can write it. So equals to prime. So this is all space, as it is 3D. There will be 3 integrals, g3 r prime, this all are vector, and gr prime. So this part dx prime gx, and this part we can neglect here, because why we are neglecting here? We can evaluate this part by using the boundary condition. Always this part is not that important, because just by putting the boundary condition of fx, because this fx is uh, x is varying from a to b, so there will be 2 boundary condition, fa and fb. By putting this boundary condition, we can easily evaluate this part. Here the boundary condition is this, that in all dimension, if r tends to infinity, then fr is 0. that essentially leads that this term is zero. So that's why we are not considering that part. Uh, just we are focusing that integral, green function integral here. So we have to evaluate this thing. So now this del operator, this del square operator, this look like in 3 dimension. We can write it like ddx square, not d equal. So in Cartesian coordinate, we know these things. And polar coordinate also we can write. But main thing is this del square operator is translationally invariant.
So this
Yes.
homogeneous part is zero. This if
Ah,
I
this part can
evaluate
be shown.
this homogeneous differential equation, if I want to solve, this
Mhm.
is a exactly Laplacian operator.
Yes.
But yeah, this del square h equal to zero, del 2
Del
h equal
square
to zero, del 2 h equal to zero here.
del 2 h equal to 0. Yes. That is
Then
a Laplacian operator.
yeah, that is the
Laplace equation.
Lagrange means where this is valid. This is the Lagrange point, means this is interesting. But they are h equal to zero, means the this
Here,
is saddle point, means the same thing on sort of.
no, this part actually, mm, we have to solve this part because this involves green function. Here, there is no green
But
function.
this part is trivial, but this is means zero that I
Yes, even
not.
this is zero because if we put that condition, boundary condition, because this green function is called actually the free green function. In case of free green function, this condition, this boundary condition is applied. So in case of free green function, always that part, that summation over hi part, this part is always zero. The kernel is non-zero. This kernel we have to evaluate. This is called kernel. I did not mention it. This part is called kernel part. This part we have to evaluate always. We see a example, the simplest example of homogeneous equation later. In that case, we can show that this part will
Okay,
not
okay,
be zero in that case
okay.
because there is a boundary condition.
Mhm.
Essentially, if we put f equal to 0, f equal to 0, that means in both boundary case, this function vanishes. In that case, also this part will be 0.
Okay,
Okay, that we can evaluate that part.
okay.
Okay, so this is translational invariant. So what we can write down from here that if r tends to infinity, this r scalar part tends to infinity, then always this will be also tends to infinity. Okay, so we can shift, we can make a variable shift from r to r minus r prime. So if we define capital R by this, then also we can say that when r tends to infinity, these r also tends to infinity. And under this limit, fr also tends to 0. So we can replace r here by capital R. So we can write down now the green equations like, so this we can write like this capital R represented that Laplacian operator written in terms of capital R, the shifted coordinate. G3R equals to, okay, because this was just r minus r prime, that is capital R. So we have just written in terms of capital R overall our green function equation. So that we can solve it easily. So now we have to solve it first. We have to evaluate that g. Then we will put that g in this green function, in this kernel. This is called the kernel. Then we can evaluate the effort. This is our procedure. So now we'll use the Fourier transform. So let me write it the general forms of Fourier transform. We are very much aware of this thing, though we are writing. So this is in case space any function. This is not this function. Okay, let me write it. with different notation. Let's say h. Okay. So we can write it like e to the power minus ik in one dimension, and this will be 1 by 2 pi dk e to the power. Okay. Also, we are also familiar with this form as well. Both 1 over 2 pi, 1 over 2 pi. These are the equivalent forms. Here I will dealing with this form. Okay. So this is our Fourier transform. So if we write the Fourier transform in the in our green function, then we can write it in k space. We'll convert this to k space. So it will be p bar. So here we have to consider the vector notation always. So this is r, and this is the reverse Fourier transform, and the Fourier transform will be just 1 by 2 pi cube d3k e to the power plus ikr. Okay, so this is our Fourier transform. Again, we know this equation will be used. Before that, we know the form of the delta function of x in one dimension. We can write that in like this. This is the form of delta function. Okay, right? So in 3 dimension, it will be just k to the power I k r. So this is form of delta function. Okay, and this is the green function. So now from here, we can write that del r square g r will be gr is this, right? This is the gr. If we operate del square operator, del r square operator, then here del r square operator, if we operate, then this del r square operate only in this term, because this is function of k. So if we apply del square operator, means there are two differentiation will be there. So essentially we will have I k square. That means minus k square. Rest part will be fixed because the function is exponential function. So it will be q d3k, just minus k square will be there due to ik. If we operate del r square here, I think this is clear. 2 times ik will be there, so it will be minus k square, and rest part will be same. Okay, so this is the form. Now we know that we have written already this equation. Delta, we have form of this part, we have form of delta function part. Now we have to just make the equivalence with these two terms. These are the equal del r gr equals to our delta function of r 3 dimension. So if we equate these two parts, then we obtain that this part is this part. So these two parts should be make identity. So k equals to 1 by minus 1 by k square. Then this part cancel and it will reduce to the delta function. So from making comparison, we can write it that in k space, the green function will be just minus 1 by k square. Now easily we can shift it to the r space. Okay. It will be, we can, I'm missing the vector sign. So it is always the vector. Okay. Now this will be 2 pi cube integration to the power I k r divided by k square. How? In this form, this is the form of gr. Just I have put in terms of green function of k, I have put the minus 1 by k square. So that's why minus appears and k square here appears. So this is form of our green function. we needed this part, right? Now we have to solve this integral. If we solve this integral, then easily we have the green function and we can evaluate the form of our function. Yes. So we have to solve this integral. So now uh, here this is 3 dimension. What is our d3k means? Actually this is dk k square 0 to infinity 0 to 2 pi d phi and 0 to pi sine theta d theta, right? So this is our the volume element for in if we integrate in 3 dimension. Okay, so we are taking like this. We are considering that there are two vector, right? R vector and k vector. But integration is done in by variable this k. K is the variable. So we are assuming this this part. R vector is acting in this axis and k is acting in random anywhere. So then this angle is theta. This angle will be phi. So now if we do the integration, then we'll obtain that this is minus 2 pi q. So 0 to infinity. If we break down the integration, then it will be dk k square. This integration will give us just 2 pi. So 2 pi will be there. And 0 to pi sine theta d theta. Then e to the power I kr cos theta. Because this is the dot product, so it will be I kr cos theta. Now this k and these are the scalar quantity divided by this k square. Essentially, this k square and this k square will be cancelled out. So this is our integral. We have to solve this integral. So it will be minus 1 by 2 pi square integration 0 to infinity dk. So here we can write this as if it's just d of cos theta e to the power I kr cos theta. We can write it just with I shift the variable d theta to d cos theta. Then limit will be changed to minus 1 to 1 and the sine theta d theta will be d cos theta. Okay. So it will be minus 1 by 4 pi square 0 to infinity dk. So this integration is straightforward. It will be just I kr cos theta divided by I kr minus 1 to 1, right? So if we put this, then we'll obtain minus 4 pi square 0 to infinity dk. It will be e to the power I k r. If it is 1, then just it's 1 and minus I k divided by I k. This I k is also there. Okay, so this is the integral. Now we know that we can write it sine kr is equal to e to the power I kr minus e to the power minus I kr divided by 2i, right? These things. So we can use this here. So it will be minus 1 by 4 pi square 0 to infinity dk, and it will be 2i sine kr divided by I kr. So I will be cancelled, and it will be minus 1 by 2 pi square 0 to infinity dk sine kr by kr. Okay, so this is the integral. So r we can take it here because it's constant. So this integral we have is very famous integral. You know this, right? So this integral, the value of this, okay, what is the nature of this function? This function sine kr by r, where k is the variable. We can say like this function is like in this way, symmetric function. But this integral value is pi by 2. But now I would like to show how this integral value is pi by 2. If we use this value, then essentially we have the answer. The answer is 1 by 4 pi r. If we put here pi by 2, then pi will cancel and if we step, so it will be minus 1 by 4 pi. R means r minus r prime. So this will be our gain function. This is easy. But this integral we should know how to evaluate. So this is very interesting to do. I would like to do this. This integral, let's see, 0 to infinity. In general, the form is, we can write it dx sine bx by x. So this is the integral. So this integral is, okay, if we want to evaluate this integral, we can write it like half of, because this is symmetric function, so we can easily write it dx over sine bx by x minus infinity to plus infinity. So if we want to evaluate that, then we can write it like imaginary part of minus infinity to infinity dx of e to the power I bx by x, right? Because imaginary part of I bx is essentially the sine bx. Again, we can write, so this integral we have to evaluate. Now, this we should write the z. Okay, let me write it x here, then we will compare it. So now, if we consider a function integral like dz sine z over z from minus infinity to infinity. So this integral is actually analytic. This if z is the complex number, essentially here z is complex variable. So this integral, this function sin z by z, this function is analytic. Only there is a singularity when z equals to 0. Otherwise, everywhere this function is analytic function. So we can take like this in z plane, we draw. Then we can take a contour like this. From minus r to r. Okay, so we can write it like minus r to r dz sin z by z limit r tends to infinity. We can write it like this. In this contour, this overall contour, here the z is 0. Here there is a singularity, but we are not taking this z equal to 0 point. So in this contour, everywhere the function is analytic function. So we can say this should be 0. Because the Cauchy integral theorem says that if there is analytic function fx, fz, dz, if that function is analytic in any contour, overall region of the contour, then it will be 0. So this is 0. So now we can break it. Let's say this is minus epsilon, this is plus epsilon, and this hemisphere, small hemisphere is called small s, and this big hemisphere is capital S. So essentially, we have break down the contour in 4 parts. One is minus r to minus epsilon, another one is small s, another one is plus epsilon to r, and last one is the capital S. So this integration, we are ignoring the limit here now. We'll put that later. So this integration minus r to r, we can write it like minus r to epsilon dz e to the power I bz by z plus r to epsilon dz e to the power I bz by z plus in the small s dz e to the power I bz by z plus capital S dz e to the power I bz by z. There are 4 parts. Okay. So now if we can choose this part very narrow, that means we can take epsilon tends to 0. Okay. If epsilon tends to 0, in that case, these two integrals can be written as minus r to r dz e to the power I dz by z. Because we are taking the epsilon tends to 0. And in this part, we can write it dz. Okay. In this means that the small s, this part, right? So in the small s, if we zoom here, so this part is like this. So here the z is equals to epsilon e to the power I theta. Okay, right? Because epsilon is the diameter radius of this contour of small s. So we can write it. If z, then dz will be essentially because z is e to, if you put z is epsilon e to the power I theta, then dz will be I epsilon e to the power I theta d theta. So if you put it, d theta e to the power I b epsilon e to the power I theta divided by z. Z is again epsilon e to the power I theta. So this part cancel out. Okay. So what remains? This part remains, but we are taking epsilon tends to 0. If epsilon tends to 0, then this part essentially vanish. If we put epsilon equals to 0, then this part will be 1. And this d theta will remain only that part. If we do that integration, this part will vanish. So and this already cancel out. So I d theta. And the limit is minus pi, 0 to pi to 0 actually. Okay, because this angle is pi here, theta is varying, and this is 0. So if we do that integration, now it is easy. So it will be minus I pi. And this part, similarly, we can put it here also. The radius is here r. Instead of epsilon, we have to put just r. Then it will be r z equals to r into e to the power I theta. Same thing. So it will be r I e to the power I theta d theta. Again, it will be e to I d, and z is r into e to the power I theta. Same thing. I'm repeating the step. Just instead of epsilon, there will be r. This part will be cancel out. R e to the power I theta cancel out. I will be there. So this part remains, right? And here the integral is from 0 to pi. But we have to keep in mind that at the end, we have to take the imaginary part only, right? So where is this? Here, the imaginary part we have to take only. So this r, if we take the imaginary part, then what happens? This b can be, okay, let me write it here, then it will be clear. So the integral is 0 to pi d theta e to the power I b r e to the power I theta. Okay. So b can be complex as is, because it can be complex also. So now the imaginary part means what happens? We can write it b as x plus iy terms. So if we take only the imaginary part, then it will be only iy. So we can write it minus I square y. So minus I square means, so this part only gives us these things, minus r into e to the power I theta. If we take the imaginary part only, real part we are not considering. So if we take only the imaginary part, then we will obtain this only. And if now if we put e to the power infinity, r tends to infinity, then this part essentially is 0. This part vanishes. So we can show it. Yes.
Here, this imaginary is okay, you are taking. But here we are considering only upper half plane of the B is
upper
real.
Half plane.
B is real.
Only upper half plane.
Yeah.
Yes.
But
yes.
here B
I
is
missed
real.
that.
Yeah. Upper half plane R equal to R is complex. R is imaginary number. So we can write.
Yes. So this is valid only in case of upper half plane. Otherwise,
the upper half plane. In the upper half plane,
yes.
The logic is that in the upper half plane we can write R equal to I alpha. R is the pure imaginary number here.
Yes.
I
okay.
alpha.
Yeah.
If I put I alpha,
B is always greater than.
Yeah. Then I square equal to minus 1. And then rest of the part is okay. Whatever you are describing.
Okay. This part was not actually given in the book, so I thought that B can be complex. Okay. This is due to the R, right? Yes.
Yeah. And another small comment is that there in the above you have written this is equal to imaginary. There you have written the equality here also. In the imaginary, this is means most accurately this is the principal value of this, means we are skipping the
this is the principal value part.
This
part is called
most accurately. We are approximating this.
Because we have to then define the principal value part. That's why I did not mention, but this part is called the principal value part.
Because we are skipping the singular point.
Singularity, and also the epsilon tends to 0. That's why we can assume this without loss of any generality.
To extract the valuable information from the integral.
Yes. So this part only contribute that small s contour. So this is valid only when epsilon tends to 0.
Means this kind of thing also remind me that means this long summation if we do 1 plus 2 means if we take the summation of all the natural integer, then it will be minus
zeta of minus 1.
The famous minus 1.
That tends to 1 by minus 1 by 12, the analytic continuation.
These are the valuable part when we are. This is not exactly equal. Means
Yes,
when
this
we
is kind of
consider
analytic continuation thing, I think.
exactly. Okay, this is a more small comment. You can.
Yes, yes, this part was also not clear to me. That's why I prepared one argument like B can be complex. Now it's clear.
Yeah, these are.
Now it's clear. The
Yeah.
R may be in upper. Yes.
This
So this
integration
then
actually came again and again. This kind of
again and again
sinusoids.
several times,
Yeah.
and that's why trivially that's just written down. This will be zero, but how this can be zero, I was little bit confused about that.
Yeah, in the complex complex energy discussion, I means took this kind of integral, one or two, three
Yes,
examples.
yes, I also think.
Yeah.
Okay, so this will be zero in that, right? Now, if R tends to infinity, then it will be power minus infinity essentially, and it will be minus infinity is zero. So this part will go away. So this part will not be there. And if we remember this overall integration is zero when R tends to infinity. So this is zero. So we can write it minus infinity to infinity because we already put that R tends to infinity. Then it will be IBZ by Z equals to I pi. So it can be written as 0 to infinity dz of no, let's say if we impose the imaginary condition in both way, then it will be minus infinity to infinity dx sine bx by x. It will be just pi, and it can be it will be 2 of dx sine bx by x pi. So it is just pi by 2. So this integral will be pi by 2. So we have already used that fact. So this is our green function. We have using this how this is pi by 2 came just discuss that part, and this is our green function. Now just rest part is easy. We know the g, we know the green function. Now we have to put that g in this equation, then fr will be obtained. So what will be fr? So now this fr is okay. Let me write it in r because already we have converted the form of green function capital R to small r, so we can write it. Okay, so in 3D. Now if we put that, then we'll obtain dr prime gr, and this is 1 by r minus r prime minus 4 pi. So this is the our uh, form of function. We can evaluate by using the green function. So this is the solution of Poisson equation. We can obtain this. So if we want to check whether this form is correct or not, then we can check it easily because we are very much familiar with some equation with the Poisson equation in case of electrostatic, right? Poisson equation is very famous in electrostatic, which is just del square phi r, where phi is the electrostatic potential. This is also vector equal to rho r epsilon naught. This rho is static charge density, and this is our electrostatic potential. So we know this solution, right? So this solution is pi r equals to 1 by 4 pi epsilon, and the electrostatic potential, the Coulomb potential. This is the Coulomb potential. So this is the form. Now, if we want to solve this equation by using the green function, we know already. This is like Poisson equation. What was the Poisson equation? Just this was Poisson equation. So here just gr is minus rho r divided by epsilon. So you can put it here. You can put it here direct. Then it will be essentially pi r will be. We have to put instead of gr, it will be minus 1 by 4 pi. Gr is minus rho r divided by epsilon. So minus minus will cancel out. Epsilon will be here, and it will be just 1 over rho is and it matches with our known result. So we can say that this green function method is absolutely gives us the right result. This is the function. So this is the way to solve the Poisson equation by using the green function. But I would like to mention that this total derivation I did, this is correct for the 3 dimension. If we consider more greater than 3 dimension, then also this analysis will be correct. But there is a problem if we choose d equal to 2. Then if we want to say that if it is d equal to 2, then what will happen? This form is correct. If it is 2, then it will be just like this, right? So in that case, what will happen that d2k in 2 dimension, it is that 0 to infinity, dk, k, and then 0 to 2 pi different. Like this, right? Only 2 variable will be there, theta and r and theta, or r and phi, you can say like this. But here the only k is here. But in case of 3 dimension, there is k square. This k square cancel with this k square, if you remember. Here there is no k square. This k square cancel out. But in case of 2 dimension, there is k to the power 1. And if we put that, then in denominator, there will be 1k. K will remains there. So due to this k, what happens in tends to infinity, when k tends to 0 to infinity, right? K varies from 0 to infinity. So this equation, if k tends to infinity, it goes to 0. So we can't do like this. In case of k equals to 2, in case of 2 dimension case, we can't write the Poisson green function of the Poisson equation just like for 3 dimension. It's not correct actually. So we can write it. I'm not going to derive that. We have to derive for 2 dimension from if we derive from scratch very beginning, then it will be okay. Then we can do that essentially. But we can't generalize the formula of 3 dimension in case of 2 dimension. We can generalize for higher dimension, d greater equals to 3. But for 2 dimension, the result will be different. In case of 2 dimension, let me write down the result for 2 dimension case. 2D case. So 2D case, it will be G2 of small r. Is 1 by 2 pi log of r. So we can give some justification that here, as there will be just 1 over k, right? After integrating that 1 over k, we'll obtain the ln k like term. So after that, there should be some ln. That's why the ln appears there. That's the reason for which we can't solve, because there is logarithmic singularity will be there. That's why we can't solve that equation. So okay, I'm not getting to that, but in 2 dimension, this will be the form of the green function. Okay, but so I would like to stop here. But other equation like Laplace equation, Helmholtz equation, or the diffusion equation, most importantly, we can also use this green function method, but that will be more rigorous calculation. So I'm not doing that. I think this is sufficient for today. The green function method to solve the Poisson equation. So this will be the ultimate result. So now let me stop here. If there is any question.
2 dimension, I could not follow means exactly.
In 2 dimension case, this is total derivation is different totally. We have to do
that
it
I
from
understand.
beginning.
Yes. Means you go
Because
step
there
by
is
step.
1 by k term is there.
Yeah. Just I want to see means
Hmm.
exactly. Just go above means where this.
Okay. Yes.
In equation wise, this part, and for 2 dimension, this is k. Okay, now go down. Means I want to follow just the equation.
Here will be 1 k term. So when we do the integration, then there will be ln k, and if there is infinity or 0, then this part will not survive them. That's why you have to take different procedure.
Okay, there will be another 1 by k. Okay.
Up to this part is correct. This will be the form. In 2 dimension also, this is the form.
This is correct. Means I want to see the exact
This
step.
this integral we can't do
Yes.
in two dimensions.
1 by k, if 1 by k survives here, then go down. If below we have 1 by k here, this is k square will be here. Okay. So go down, go down. So here sin kr by k square is exact equation. Exact integration we have to evaluate.
No, we can't go up to there actually, because here there is a logarithmically divergent. This integral is logarithmically divergent because this ln appears now. So when k tends to infinity, this total integral will be diverged.
K is constant, means up to theta k is constant, no?
And up to theta we can do, but
we can do. That's why
when we want to
this
evaluate
final
this
point
part,
is, yes, final point is integration 0 to infinity dk by k square.
Here will be k square.
Yeah, yeah, that point we stuck. Means I want to see
Yes,
point.
we can write like this.
Okay, dk
So
by,
this part,
yeah, yeah.
dk by k. So there will be ln k, and if when
I want to
k tends to
see,
infinity,
means it is a double
double integral.
singularity. Yeah, yeah. If
This
we
singularity is removable, we can skip that. We can solve that part.
yeah,
Though
means
there is a singularity.
means I am thinking in terms of if we expand this in terms of Lorentz
In
series.
sine series.
Lorentz expansion.
Lorentz series. Acha,
Lorentz series. Lorentz series.
In Lorentz series,
Then
also,
we can easily identify the, for 0 to infinity, we can easily identify the means simple pole.
simple
Okay,
pole
there is 1 by
there
k
equal to 0.
coefficient. 1 by k coefficient.
Hmm.
Then 1 by k coefficient exactly equal to the I into this 2 pi I into that residue.
That residue. C, then that will be c
Yeah,
minus
yeah.
2.
Yeah.
Because k square.
Yeah, that point we can do, but here problem is that this integral is 0 to infinity, not minus infinity to infinity. Because this is a odd function. If this is dk by k square into sine kr, earlier it is okay. Okay, means I want to see that if we can evaluate it in complex
By using actually this
integral.
sine k by k, this part we can evaluate. But if it is k square, we can try by using complex contour integral.
Yeah, complex in complex, we have to just get the, means we first
residue for the minus 2
yeah,
term.
yeah, we have to just rewrite it in terms of complex term. Just you did here, you do it here.
This imaginary part.
This
This
imaginary,
integral
like that. Means
but in
this step we can
that case, this will be not 0. This will be not 0, I think, because there is a pole.
There is pole, means pole is
But we
always
can skip
at
that.
the center. We can skip it.
Skip that.
But you know the result. This is ln z, no? This is ln.
Yes, this is ln z. We can do that also.
Okay, okay, okay.
We can do by just we have to make a shift from k to mu, something like. But this is more rigorous calculation. But we can think like this is called basically if k is 0. Here what happens is, as k is infinity, this essence. Okay, you can think like this, like when it is more than 3 dimension, if it is greater than 3 dimension, d is greater than 3, then what happens? Here will be k will be in here, right? If it is 4 dimension, then 1k will be there. Okay. Yeah. So if 1k is there, then also it will be not, it cannot be solved like this. Then this k and this k will cancel out. So in that case also we have to take another method. But after that, after doing that method, we will, after solving, the result is same. The 3-dimensional result and greater than 3-dimensional result are same. But in case of 2-dimension, the result will be different. The log is appearing there.
Okay. Means every dimension, the calculation, the integration is different.
Integral is different. We have to do that integral basically. This up to that part, this is correct.
Okay.
Ring function is same, but solving ring function, that method is different.
Okay. And you can share the 2-dimension or other dimension calculations. Okay. Then we can.
Okay. I can share that.
We can go through it. Yeah. Yeah. It will be helpful.
The main method is this thing like that we have to break that G in singular part and the regular part.
Yes, yes.
Then
Yes.
we can do that.
Mm-hmm.
And in regular part we can neglect, and from singular part, in case of 2 dimension, there will be 1/2 pi ln r.
Yes, yes. Yes. Okay.
Okay. Should I stop sharing?
Yes, I think.